Okay, so off we go. So last time we were talking about these deformation things, and remember the idea is we went through some details, and I won't go through those details again, but if everywhere in the equation you replace z with 2z, like I've done there, right? Then you can take this point of view that effectively points that used to work don't work anymore, but if you cut their z-coordinates in half, they do. And so effectively the punchline is that you're squishing the surface by a factor of 2 in the z direction. And the little sort of pithy little sort of generalization, summary of the generalization of this is that in some sense whatever you do to a variable in an equation, sort of the opposite happens to the surface. In some sense, the solutions have to undo what you do in the equation, in some sense. Broad strokes. Okay. So here's another couple of examples of this. Let's look at, here's one that we already know. Again, rho equals 1, easy to understand, gives me the unit sphere, no problem. Okay, how does that help me understand this equation? Now I want to emphasize, presumably we don't come into this question already knowing what this looks like, right? And, well, let's see here. It's not rotationally symmetric around anything because A, B, and C are presumably different. So X and Y don't appear in that special form exactly, precisely. And again, all that rotational symmetry stuff is very delicate. And it has to be just exactly so, and this just doesn't cut it, right? So I don't have any foot in the door on this, except perhaps, maybe, if I'm able to somehow relate that equation to this equation, then I can hopefully analogously figure out how to turn the known surface into the desired surface, right? So that's our strategy, and the deformations are actually pretty clear. This x just gets turned into x over a. Right? Everywhere in the left equation where there was an x, I replaced it with x over a. Likewise, the y, everywhere it gets replaced with y over b, and likewise z gets turned into z over c. So within the algebra, I'm in some sense kind of dividing by these A, B, and C. And so the result then is that geometrically that we are effectively stretching correspondingly in the appropriate directions by these factors A, B, and C. Right? And so that's why our original unit sphere, being stretched by these different amounts in these different directions, turns into, well, you could probably imagine that we would call this an ellipsoid, because in the same sense that a circle deformed by stretching is an ellipse, this is now a sphere deformed by stretching. And so we use the analogous word ellipsoid. Okay. All righty. Now there's one little algebraic landmine I want to point out for y'all. In general, let's suppose you find yourself looking at an equation that says, x squared plus blah, 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 that you sort of know, and that on the right, your new equation is, let's say, x squared over 4, and then again, blah, 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 whatever. It's a mistake to think that this results from replacing every x with x over 4. That's just not what's going on here, right? Because the x over here, if you look at this x, what happens to the x? It gets squared, right? So whatever I replace x with, the entirety of what I replace x with needs to get squared, and that's just not what this is. Right? So that would be a mistake. In order to make sense out of this in the way that we have been, what I need to do is to rewrite all of this. I'm just going to rewrite the new equation as something squared plus dot, dot, dot. And now let's ask us, what would I have to put here to make that, oh gosh, I wanted a different color, to make this term equal to that term. And I think you can persuade yourself pretty quickly that that needs to be x over 2. Right? So the thing that I replace x with is x over 2, not x over 4. And written in this way, you see that everything that I replace x with, x having been squared over here, everything that I replace x with, indeed, is actually being squared as it should be. So make sure to be careful about this. Don't actually get your stretching factors wrong because of algebraic misinterpretation or whatever you want to call it. Okay. All right. A couple more examples. These I'm going to mostly wave my hands at. You can see that here in this example, the x is being replaced with x over a. Indeed, the square is happening to all of that, right? So that's okay. Y with y over b, etc. So again, we have stretching happening here. There's a stretching happening in both of the horizontal directions. And if you think about it, our initial paraboloid has circular cross-sections. The horizontal cross-sections are all circles. In our regular paraboloid, you can see the rotational symmetry right there in the equation. Right? So if those circular cross-sections, when you stretch the whole thing by various different factors, those circular cross-sections get stretched in the x and y directions, and so those circular cross-sections turn into ellipses, and thus this is called an elliptical paraboloid. It's a little terminology. Likewise, recognize this as a hyperboloid of 2 sheets that we discussed before, and when you stretch it around in various different directions, the result is an elliptical hyperboloid of 2 sheets. Okay, same basic idea. Okay. All right, and the book has some various other examples. Always remember you should be kind of looking through the book as I go through, in my notes, and I'm not going to cover every single thing that's in the book, but you are responsible for everything that's in the book unless it's explicitly excluded on the content syllabus. Okay. All right. So, on to section 2.3. You may notice we're skipping section 2.2. It's not part of the course. It's another one of these tough choices that there's too much stuff. It has to get covered. 2.2 is very important material from a mathematician's kind of rigor point of view, and that's just not really what this course is, so we just don't have the time to do that. Okay, so derivatives. First thing you need to know about multivariable derivatives is that there's more than one of them. It's not like single variable calculus. In single variable calculus, there's the singular derivative. Here we're going to have several, and depending on how you count, easy 3 of them. And depending on how you count, maybe 4, 5, or 6. So something to be on the lookout for. The reason we use the single word derivatives to describe all of them is because they all do have a huge important point in common, and that is they all relate input changes to output changes. And so it's a good idea to be on the lookout for that. And all the different derivatives that we're going to talk about, think about where in this understanding of what this derivative is, where is the input change, where is the output change, and how is this thing relating them? And it's different in all the different examples. Okay, I'm going to start with partial derivatives. Some of y'all may have seen these before. Possibly. If not, it's okay. Yeah? Oh, I'm sorry. Okay, no worries. Is everybody good? Yeah. Okay. So good news. Partial derivatives are super easy to compute. It's one of the things that makes them so useful. It's so easy to work with. It's very nice. They are very familiar and satisfying. They're going to end up being a lot like single variable derivatives. In a way, they are technically single variable derivatives. We'll talk about that in a minute. And another good reason to talk about them now and first is because the book does. But with that in mind, I want to point out, I wish the book didn't. I wish the book did things in a different order, because I think there's some significant disadvantages to starting with partial derivatives. I feel like when you have several things to discuss, whichever one you start with gets taken as this is the fundamental, this is the default, this is the natural, this is the one that you should fundamentally think of, etc. And frankly, when you leave this course, I hope you don't think of partial derivatives as being your fundamental point of view on what derivatives are. When you leave this course, if someone says, hey, I got a multivariable function and I want to know what's the derivative, I hope you will not ask them, do you mean partial derivative? Because it's really a niche kind of point of view on differentiation, and there are much better, broader examples. Okay. All right. So just keep that in mind. Don't put all your eggs in this one basket here. So here's what it is: a partial derivative. I'm just going to describe the process for computing partial derivatives. You're going to start off by identifying one of the input variables to remain a variable, and then you're going to hold all the other variables constant. So, seems a little unfair. Can you just declare variables to be constant? Well, it's your calculation, and so, yeah, sure. I mean, we're defining a new thing here, and we can choose to do whatever we want to do. Now, that said, that does kind of limit the interpretations, right? If the thing that I'm about to define requires making an outrageous assumption that only one of the variables is ever allowed to change, you can see that this is going to have limited interpretation. Which is one of the reasons one of the reasons that I don't want to start with this. But anyway, here we are. Okay, so we're going to hold all the variables constant except for one. As a result, then, what had been a multivariable function is now a single variable function. Right? There's several variables, but most of them are required to never change. They are effectively constants. There is therefore really only the one variable actually remaining a variable. And once you have a single variable function, well, we know how to take derivatives, good old regular old Calc 1 derivatives of that resulting single variable function. Okay, so that's going to be our process. I'm going to show you some examples in a couple of seconds. Real quick on notation, just so we can, get the things written down. Here's the primary notation for partial derivatives. You'll notice that this looks a lot like Leibniz notation, right, for single variable derivatives. One of the big differences being that this symbol is not a D. Very importantly, that is not a D. It looks kind of like a D. It's supposed to be reminiscent of a D, but very importantly, it is not a D. You cannot use a D in place of that symbol. That would mean something different, and it's not allowed. Okay. All right. And likewise, a lot of people get confused and think that it's a Greek letter delta, but it's not delta either. So it's just a new little thing, and I'm going to confess that when I first was learning this material and I first encountered that little symbol, it didn't feel natural writing it, and I actually spent, several minutes kind of deciding, all right, I'm going to be an inside-out kind of spiral. Some people like to do it, spiraling inward instead of outward. You got to decide what kind of person are you going to be, right? And, fill up a page, make 50 or 60 of them, make sure that you can make them respectably. You don't want to accidentally, make them like this. That looks like a 0, right? That's not good, right? So think it through. All right. Okay, so let's compute one. Here we go, our very first partial derivative. And let's see here, starting with a partial with respect to y of this great big monstrosity. And right off the bat, I'm scared, right? Because there's three separate factors. I can see the product rule coming up several times. One of the factors is a composition with a product inside of it. This looks like it's going to be a nightmare tedium. And it's not. Because you got to remember, y is our only variable. That means this y squared is a function, but x is a constant. That means e to the x is a constant. And furthermore, with z being a constant, all of that's a constant. And so all of this here is all great big constant, right? All of that, practically all of the function is a constant. There's really only one little teeny tiny itty bitty little factor in there that's actually allowed to change, right? And so in the same sense that it's easy to take a derivative of k times y squared, after all, that's really what this is. Some constant, let's call it k times y squared. And that's an easy derivative to compute, right? So that y squared, taking the y partial, I just get 2y. And the multiplicative constant just comes along for the ride. Nothing happens to the multiplicative constant, aka my k. It just sits there. So easy, done. And then shuffle factors around if you're so inclined. What do you think? Everybody all right with that? Very convenient to compute partial derivatives. Okay. Let's do another couple of examples. Here we're going to be taking an x partial. Okay, so that means, and you have to make a conscious effort to think about this, that means that y is now a constant. That means that y squared is a constant. And so even though at your first glance you might have thought, function to the power of a function, logarithmic differentiation perhaps, something along those lines, right? Nope. This is a function to the power of a constant. And we have a rule called the power rule, that whatever that constant is, you multiply by it out front, you subtract 1 in the exponent, and don't forget the chain rule, right? And so, easy. Straightforward. Everybody happy? All right, another quick example. Here, partial with respect to z. There's my z. Again, at a quick glance, it looks like function to the power of a function, but x and y are constants because z is our only variable because I'm taking a partial with respect to z. So this is just a exponential. And the derivatives of exponentials are easy. And it's an old Calc 1 differentiation rule. I hope you all remember. Is that cool? Nothing to it? Okay. All right. Okay. So what do we have so far? We have I'm going to loosely call this a formula for how to compute partial derivatives. We have notation for how to represent them. We have a couple of examples of computation under our belt, but one thing I have not given you any of at this point is motivation for why we would ever be interested in this thing, right? What does a partial derivative have to do with anything in the real world? It's our next question that we want to consider. And I'm going to start with the idea of geometric interpretations. What does a partial derivative look like? Now, thinking back to single variable calculus, again, you see the derivative, the formula gets written down for a derivative, and then very quickly the question comes up, what does it mean geometrically? And you get this very satisfying, it's the slope of the tangent line. And then now, y'all know that I'm real big on which type of pictures are we looking at, right? So a clarification, single variable derivatives are slope of the tangent line to the graph. It's only the graph, right? Specifically the graph. Okay, so now that we're in a multivariable context, we're going to be looking for some analogous kind of interpretation, but now we have multiple different kinds of pictures that we might be looking at a graph. We might be looking at a level set. We have several different kinds of pictures we might be looking at. Right? So make sure to keep in mind, make a conscious effort to keep all this straight in your mind. You have to kind of, do your own sort of mental bookkeeping. What we're about to start off with, and we are, you'll notice, going to start with graphs. What you're about to see only applies to graphs. We're about to take our first step into the calculus of graphs. And please, please, please don't conflate the calculus of graphs with the calculus of level sets, which is a totally different thing. Right? So, something to keep in mind. Okay, so graph. Here you go, graph, right? We're taking the values of a function, setting equal to a new variable. Here's our function, by the way. 2 input variables, 1 output variable. And whatever the output is, we're going to call that output Z to form the graph. All right. Now, do keep in mind that, let's see here, having, as we do, 2 input variables, the domain being as it is R2, X and Y are variables. You can kind of see the domain, the XY plane. You can kind of see it down here. It's kind of the footprint, I don't know what you call it. Anyway, it's the XY plane, right? In 3 space. This is a slight abuse, but this is pretty good for geometric intuition purposes. I'm going to view the XY plane in space as being kind of like my domain. My target, well, let's see here. My output variable is called Z, so my target is represented by this variable Z, which again is the other axis there. So you can kind of sort of see the target. Now, reminder, the graph itself is neither of these. The graph itself is a surface that lives in this weird 3-dimensional space that's not the domain. And it's not the target, right? This 3-dimensional space we made up just for the purpose of being able to draw the graph, right? But anyway, there it is, and so domain and target you can see in relation to the graph there. All right, now when I say I want to make an interpretation of a partial derivative, I need the partial derivative to be evaluated at a particular point living inside of the domain. I'm going to imagine some particular point down there in the domain. And so when I say I want to compute the partial of f with respect to y, specifically I want to know what is that partial at this point a comma b in the domain. Okay, is everybody with me in the setup here? Haven't really answered the question yet. We're just kind of setting up the question. Right, okay, cool. Okay, so here's the good news. The process of computing a y partial has 2 steps. And very conveniently, each of those 2 steps, we already know what it looks like geometrically. So really all I have to do is put those pieces together. And here we go. Step 1, when you're taking a partial derivative, you have to fix the other variables. Now, reminder, we're taking a partial with respect to y. So y is our remaining variable. Y remains a variable. That means that my other variable, there's only one other input variable, is x. That means x has to stay constant. Keeping in mind that we start at this point a comma b, where x is a, that means x is going to have to stay at that value a. Right, so for the purpose of this computation of the y partial, x is fixed constant at a. In other words, I'm looking only in this vertical cross-section of my initial graph. Right, and keep in mind my initial graph is this whole surface. But now that I'm fixing x equal to a, all that really remains is that cross-section curve. Yeah?
There's no way to say anything about the whole surface. You have to keep it relative to some point in your domain which maps up.
So a partial derivative can be defined everywhere in your domain, right? But it's just if you want to compute the value of the partial derivative, you have to decide first where are you computing it, right? And once you've decided where you're computing it, then the geometry sort of follows from that choice.
Okay.
Yeah. Did I answer your question?
Yeah, I was just. Yeah.
Okay. Yeah. Cool. Okay. Now let's think about this cross-section curve here. I claim that this cross-section curve is actually relevant to something we already know, we've already discussed. Here's how. Notice that on this curve, we have these points all have kind of heights, if you will, above the xy plane, those heights being z. And notice that those heights, where I am, in some sense, on that curve, only depends on y. Because after all, x is constant, right? So for any given y, thought of as the input, we get a z vertical, thought of as the output. I have height as a function of horizontal input variable. I have a graph. This cross section is literally the graph of the function. Let me write this down. This is the graph of the function. Let's see here. What I chose z is now f of a comma y, and so let's see. Let me highlight appropriately. What I have highlighted in orange. This is the single variable function of only y that results by fixing the other variable x at being a. And this curve is the graph of that single variable function. Namely, this single variable function that I get by holding all the other variables constant. Now, the reason that's relevant is because notice the very next step that we're going to take is to take the derivative of that single variable function. How can I interpret the derivative of that single variable function? Well, conveniently, I am looking at a graph of that single variable function. And the derivative of a graph, the derivative of a function when you're looking at a graph, the derivative is the slope of the tangent line to that graph. So there's our nice little punchline. Let me just do it like this. Here we go. So the partial with respect to y, it's the slope of the tangent line. It's the tangent line to the graph of the function, but specifically, of course, in the direction where x is held constant, namely in the y direction. Nice little pithy description, geometric description of how to interpret the partial derivative. Everybody on board? Yeah.
In this situation, you're saying change the function, you have to change y. Like, could you say z in this case, or is that like bad?
I'm not sure. What do you ask?
Instead of saying I think it's df dy, you say dz dy.
It depends on what's been set up in the statement of the question. Let's look at how we set this up. The way I have this set up, I said graph and I said z equals. That was all. This is all part of my setup. And so with the understanding that z is the name that we're giving to the output values for f, if you wanted to rewrite f as z, I think that'd be reasonable in this case. Yeah, absolutely. Cool. All right. Okay, so notice that what I have here is a series of pictures and resulting interpretations as I go through the process of computing a partial derivative with respect to y. What I want y'all to do as a suggested exercise, and you don't have to, right? Not going to turn it in, but I think a really healthy suggested exercise would be to go through analogous reasoning to make sense out of the partial derivative with respect to x. The pictures are going to be a little different. Highly analogous, but very importantly different, right? And the punchline you're going to get, and I hope this is no surprise, you're going to get that the x partial is the slope of the tangent line to the graph in the x direction. Right? And the pattern is, very nice, very convenient. The y partial, slope in the y direction. The x partial is the slope in the x direction, exactly as you would sort of expect. Nevertheless, good exercise here to think that through, persuade yourself that that's true, draw the corresponding pictures, and make sure that you understand every step of that analogous argument. Okay. Everybody okay? Everybody see what I'm proposing here? Okay. All right. Now, all of that was for graphs. And we like graphs, and that's cool and everything, but sometimes we can't draw graphs. So let's suppose that I'm looking at this, I recall I like this term, literal picture, where I draw the domain here, and then I draw the target here, and then the function that goes from the domain to the target I represent by, that's supposed to represent the action of green points moving over and falling on top of blue points. Right? So literal picture. How would I, where's the partial derivative in this picture? What's my geometric intuition for partial derivatives here? This is going to be disappointing. It's not going to be a slope of a tangent line because tangent lines would require there being a curve. I don't have a curve to talk about a tangent line of. So in this context, when you're looking at this kind of a representation of a function, partial derivative does not say a thing about a slope of anything. So again, be careful with that, right? This whole business that derivatives are slopes that's only in the graph context, right? In this context here, no, it's going to be something totally different. Now, what I'm going to do to interpret the y partial in this case is recall that we have a different interpretation of single variable derivatives. Single variable derivatives are factors that you can multiply by input differentials to get output differentials. This is just kind of a reinterpretation of an old fact from Calc 1, right? And now in this context, though, where are these differentials? Where is my dy? What does dy look like in this picture? And, well, dy, let's see here. We're taking a partial with respect to y here. That means x and z are not allowed to change. That means that whatever z is, it's staying that. And whatever x is, it's staying that. So we are confined to that line right there in the domain, this line parallel to the y-axis. And dy then is just literally representing how much we move along that line. So dy represents how much we move in the domain with the understanding that we're only allowed to move exactly in the y direction. That's what dy is. And then our df, how much does the function change? Well, when you move by some amount in the domain, df is our linear approximation of how much resulting movement we get in the outputs. And so here's your interpretation of the partial derivative. The partial derivative is the factor that you multiply by this input differential to get this output differential. And that's pretty unsatisfying, I think. I can't point to it, right? There's nothing in what I've described here points to there it is. There is the partial derivative. Now it's just not a thing like that in this kind of a picture. You can only kind of see the partial derivative and how it relates that green differential to this blue differential. So keep that in mind. This is it is what it is, and don't overinterpret and misinterpret. Where's my pen? Here it is. Okay. All right. Moving along. Let's talk about level sets. Now this is a dangerous one because these various level sets that I've got drawn here are curves that do have tangent lines. And so you're going to feel this temptation, when the question comes up about a derivative, partial derivatives is kind of a derivative, and you had it drilled into your heads in Calc 1 that derivative means slope of the curve, or slope of the tangent line to the curve, and there's a curve. So you're going to be tempted to say that one or the other of these partial derivatives or something is the slope of one of these lines. And it's absolutely not. And again, this is I know I say this a lot, but I want to minimize the number of people who make this misinterpretation. The calculus of level sets is what we're talking about here. How to geometrically understand calculus, namely derivatives, in this picture where we're looking at level sets specifically. And it's just not at all the same as the calculus of graphs. So again, don't think slopes here. It's just not slopes. It's certainly not a slope of one of these level sets themselves. Okay. All right. Now, all of that said, how do I interpret a partial in this setting? Let me momentarily zoom in here. Mostly for my artistic convenience here, I'm going to look at this curve. Oh, man. Let's try that again. And then this curve. There's a couple of level sets. Again, there's different ways that you can think about level sets. My favorite metaphor myself is to think of them as contour lines on a topographical map. So each level set represents an altitude. Maybe this represents, 600 feet of altitude, and the next contour line 700 feet, and the next contour line 800 feet, something like that. Okay. So looking at these two lines, let's consider two different ways that I could climb the 200 feet between these lines. And, well, if I go in the x direction, I only have to go that far, and that's not very far at all. On the other hand, if I were to climb instead, maybe there's a different trail and it goes off in this direction, well, then that would take me much more distance. To gain the same 200 feet of altitude, I'm still crossing two contour lines. It's still a 200-foot elevation gain, right? So now looking back at the algebra that we have here, and let's see here, let me do like that. This little change in x suggested by that notation there is a teeny tiny little change in x, and that's in the denominator. Right? So you're gaining 200 feet over a short distance if you go in the x direction, and that means that this partial derivative you would expect to be pretty large. In other words, you'd expect that to be a pretty steep hike. Right? Whereas, by contrast, this... Oh, whoops, missed it. There we go. The little y change, well, I've got to move pretty far in the y direction to gain those same 200 feet. So I have a relatively large denominator, you might say, and so you'd expect the y partial to be small because it's not that steep in that direction, because it took me a long distance to gain the same altitude. So what you get out of this is a kind of a loose interpretation, not a precise geometric picture, but kind of a loose feel for how partial derivatives look on the level set context. Roughly speaking, whichever direction you're looking in, maybe the x direction, maybe the y direction, in whichever direction you're interested in, the closer the lines are together in the relevant direction, the larger that partial derivative is. And the farther apart the lines are in the relevant direction, such as in the y direction, the farther apart the lines are, the smaller your partial derivative is. Now, I can't actually quantify this because I don't have any scale here, right? How far of a horizontal distance is this right here? I don't have a legend on this graph, right? I don't know what the scale is in the x and y directions. I don't have it written down anywhere what the altitude difference is between these contour lines, so I can't make this precise. But generally speaking, closer together means steeper, and thus a greater value of the partial. Is everybody happy with that? And again, don't overinterpret. I mean, this is, again, kind of disappointing. It is what it is. Yeah?
What is that, gray cross in the middle that you're, measuring to?
What is the what now?
The, gray cross in the middle.
The gray cross. Oh, yeah, I would. That was just a reference lines so that I could, I wanted to be able to talk about which direction is the y direction, for example. So I needed that line there just to help me not have to eyeball what I mean by parallel to the y-axis. That's all.
Okay.
Think of it as like grid lines on graph paper, something like that. Yeah. Okay. All right. So 3 different interpretations of partial derivatives in these 3 different geometric representations of the function. Okay. Next thing, linear approximations. Y'all have seen single variable linear approximations. Oh, by the way, real quick, everything I'm going to say about linear approximations is on the assumption that they exist. That seems silly, but it turns out that there's actually a lot of subtle and sophisticated work that has to be worried about to show that linear approximations actually exist. And so for the moment, I want to sweep that under the rug entirely. We're going to assume that they exist, and then we'll worry about some of that formality after, and we're not going to do a Math219 take on it. We're going to do a little bit more practical take on that. All right, so assuming linear approximations exist in single variable calculus, there's the formula. I'm sure you recognize it. Now, what is it that makes that the linear approximation? Well, there's different ways that you could think about it. What I think is the crisp, satisfying, at least in this, what we're about to do, interpretation. This is the unique function of this form, the unique degree 1 polynomial that agrees with f in terms of value and that agrees with f in terms of derivative at the given point A. So, assuming that linear approximations exist, this formula gives the same value as f, it gives the same derivative as f. It's doing the best possible job of impersonating f at the point A. So, thus the term linear approximation. Does that make sense to everybody? Plausible? Okay. So the main purpose of this little discussion, I know y'all already know the single variable calculus of it all. The main purpose was to establish that this is how we're going to think about linear approximations. They're first degree polynomials that agree with the target function in value and in derivative. Okay. So let's ask the question now: what would we do if we wanted to do the same thing for a multivariable function? Note here, multiple variables in different input variables. I'm just going to write down the formula, justify it. Well, I'm going to say a few things, justify it, but here it is. This is the linear approximation. In the same sense, in the sense that this is the unique degree 1 polynomial that agrees with f in value at the point A, and that agrees with the, oh gosh, I got to be careful how to say this. I can't say the derivative. There's a bunch of different partial derivatives because we have a bunch of different input variables. So this is the unique one that agrees with f for all of the partial derivatives. And again, there will be a unique such function if it exists at all. And this is the formula for it. This just makes it work. Now, I'm going to leave it as an exercise for y'all to confirm that this formula does what we claim that it does, namely that it has the right value and that it has the right derivatives. I'm going to walk you through kind of how to do it. It's, by the way, mostly just a matter of plugging in. The one little tricky bit is when you take the derivative to compute the various different partials of L. And for that purpose, I'm going to start by coming back up here and noticing that f prime of a right there, a lot of people misunderstand and think that this is a function. And it's not really, because while f prime was a function, I plugged a into it. A is a constant. It's just some number, right? It's not a variable. It's a number. And so f prime evaluated at the point A is ultimately just a number. And so this f prime of A is a constant. And as such, I'm going to highlight it in gray. This is just a constant. So likewise, looking at our new linear approximation formula here. Whoops, missed. Our new linear approximation formula, looking at, for example, this thing right here. That, too, is just a constant. It's a scary-looking constant, right? But it's just a constant. F was a function. The partial with respect to x in is a function. But when I plug in the point A, it's just a number. It just sits there, right? So when you're taking the derivative of L, don't forget that this partial of f with respect to x in, evaluated at A, that is just a constant. For the purposes of differentiation, you treat this as a constant because it is literally a constant. So keep that in mind. Everything else is just a matter of kind of plugging in. And again, I hope you'll take me up on my suggestion to confirm that this function does what it's supposed to do. Okay. All right. Let's see here. Let me do a little bit of a rewrite. Look at this part of our function. This is not the whole linear approximation, but that's it's the bulk of the linear approximation. And notice it's a sum of products. Good general rule of thumb, whenever you find yourself looking at a sum of products, entertain the possibility that it might be naturally interpreted as a dot product. And that's exactly what's going to happen here. We have here a bunch of factors being multiplied by a bunch of other factors. And multiply and add, that is literally a dot product. You're going to notice pretty quickly that these blue factors are literally the coordinates of this vector x minus a. So not only is this structurally like a dot product, the blue factors are literally the coordinates of x minus a. And so all that remains is to figure out how to think about these green coordinates, right? What are we going to... if I want to make this a dot product, I need these green factors to be the coordinates of a thing, the coordinates of some vector. So we're going to define a new vector, just for notational convenience, as the vector whose coordinates are those green factors, thus making this literally, exactly, actually a dot product. And this makes this expression much easier to write down. All of this purple stuff here, now it's just a dot product. That's pretty neat. Now, that said, this new thing, this new green vector here, this is brand new. We've never seen that before. It is, for the moment, just a notational convenience. We call it the gradient. There's going to be good reasons to think of it in those terms coming up soon. Here's the notation that we use. I emphasize that this little triangle right here that we use to denote this, the pointy end goes down. And that's important. That pointy end goes down. If you draw it with the pointy end up, it means something completely different. Right? So please be careful about that. Pointy end down. Okay. All right. And then, literally, now all of this clutter up here now neatly compacted as gradient dot x minus a. Okay. Let's see here. How are we doing on time? Oh, we are out of time. Okay, well, so we will draw the line right here, starting with an example next time. See y'all later. Have a good one.